In this video, I'll be going over a question related to the learning outcome. Describe waves in terms of their wavelength, amplitude, frequency, speed, and intensity. But the question will go on to involve a problem related to the learning outcome. Identify nodes and antinodes on a stationary wave. And so this is a good example question that covers a number of different learning outcomes, all related to the physics of waves. It comes from ACE Physics Syllabus Code 9702, paper 23 from May-June of 2011. Question number 6. It reads, a transverse progressive wave travels along a stretched string from left to right. The shape of part of the string at a particular instant is shown in figure 6.1. It says the frequency of the wave is 15 Hertz. For this wave, use figure 6.1 to determine the amplitude. The amplitude is the displacement, the maximum displacement. And so we can see on the graph that the maximum displacement is this point here that's labeled P. And we have to be able to sort of deduce how much does each division on the scale sort of represent. So it's displacement in millimeters, and if this is 6 millimeters, and then up here is 8 millimeters, and there are 5 squares in between, then each square is 0.4 millimeters. And so we could count up 6.4, 6.8, 7.2, 7.6, 8.0. And so because this is sort of the first square underneath 8, that's 7.6 millimeters. 7.6 millimeters is the amplitude of the wave. It says the phase difference between the points P and Q on the string. Point P is at this crest. Point Q is at the trough. Those are points that are half a wavelength away from each other. And so the phase difference there is 180 degrees, right? There are 360 total degrees of phase in a wave. And so when points are half a wavelength apart, that's a phase difference of 180 degrees, or pi radians if you prefer. The speed of the wave. The speed of a wave, v is equal to, velocity is equal to wavelength times frequency. We're given the frequency up here, and we can read off the wavelength from the graph. So here the wave starts at 0, and it begins to repeat right at 80 centimeters. You can also see from this crest here to this crest, it goes from 20 to 100, and so that's also 80 centimeters, another way to read the wavelength. And so the speed of the wave is going to be 80 centimeters, which is 0.8 meters, times the frequency, 15 hertz, which is the same thing as reciprocal seconds. So meters per second give us meters per second of the speed. 15 times 0.8, 12. 12 meters per second is the speed of the wave. The question goes on to say, the period of vibration of the wave is t. The wave moves forward from the position shown in figure 6.1 for a time of 0.25 t. On figure 6.1, sketch the new position of the wave. So this is a quarter of the time period. All right. So the period, remember, is the inverse of the frequency, but because we already know the wavelength is 80 centimeters, we can kind of think about, well, if it were, a time t later, then this point P is just going to be sort of right over here. Or rather, the wave would have traveled sort of over to here, right? This point is sort of oscillating on the spot, right? It's a transverse wave. But the wave would have made it over to here after a time t. So we basically need to sketch what the wave is going to look like a quarter of that time later. So it's going to be a quarter of the 80 centimeter wavelength. Well, these are kind of convenient numbers for this purpose. And so here we have 20, 40, 60, 80 centimeters of total wavelength. And so a quarter of 80 is 20 centimeters. And so we can kind of think about the wave, a quarter of the time period later is going to have a peak right there. The crest will be right there at 40 centimeters, right? The wave has moved 20 centimeters in a quarter of its time period. And so every sort of point on this is going to kind of shift over by 20 centimeters. So you can think about this point right here that's at 40 is going to be at 60, right? This point here that's at 0 is going to be here at 20, and you can kind of see the waveform that we're getting. So point Q down here is the wave would have moved over to here. Again, the particles will still be oscillating, you know, like this, but the wave is going to move along like that. All right, so this point right here would be over here, and this point here would be there. All right. Oh, I kind of missed my mark there. All right, ignore that. All right, and so you would want to take your time to just do your best to sort of, you know, sketch that as best you can there. All right. But by marking a few points there, you can kind of see, and so that would be the new position of the wave a quarter of its time period later. The question goes on to include a question about stationary waves. So it says, part C, another stretched string is used to form a stationary wave. Part of this wave at a particular instant is shown in figure 6.2. All right, they've got 2 points, X and Y labeled, and we can kind of see there's a waveform there. The points on the string are at their maximum displacement. State the phase difference between the particles labeled X and Y. Well, with a stationary wave, we have sort of all of the parts of the string right here are moving in phase together. They're moving up and down sort of like this, right? And the nodes don't move at all, right? And so these are the antinodes, those points where there's going to be maximum displacement. And so X and Y are sort of both in phase. The phase difference is 0. There is no phase difference. 180 degrees is the phase difference between particles that are occupying adjacent sort of loops on this, right? And so as this transverse wave is sent out like this, let's say it's being reflected, you know, right here, and so we kind of can think about the reflected wave as coming back like there, and the interference of the incident wave with the reflected wave is what a stationary wave is. And so we can kind of think about these as like loops, and particles that occupy adjacent loops are always 180 degrees out of phase with each other. So like, well, all these particles are moving up, all these are moving down. So they're 180 degrees out of phase. So any particles that are sort of on the same loop or another loop over, so not the next door neighbor loop, but the neighbor after that, right? So another loop over from that, then while all these particles are moving up, all these particles are moving up. And so they would be in phase. And so X and Y are both in phase. There's no phase difference between them. If it were, say, a point X and Z down here, then those would be 180 degrees out of phase. So that's one way to think about phase difference in a stationary wave. The particles are either, you know, in phase or they're out of phase. Explain the following terms used to describe stationary waves on a string. An antinode, like I said, would be places right here, and here, and here. Points of maximum displacement. So an antinode, points of maximum displacement. And then a node would be points that I'll label N, where there would be no displacement. The question goes on to say, state the number of antinodes shown in figure 6.2 for this wave. And so we see an antinode here, here, and here, and so that's going to be 3. The last part says the period of vibration of this wave is, that looks like the Greek letter tau. On figure 6.2, sketch the stationary wave 0.25 times tau after the instant shown in figure 6.2. Well, with the stationary wave, the particles just kind of move up and down, right? And so right here we see like this point down here at this moment. And so 0.25 times the time period, this particle will be here. Half of the time period, it's going to be all the way up here. 0.75 or 3/4 through its wave cycle, it'll be back here. And then after the entire period of the wave, it's back where it started, right? And so that's what sort of characterizes the wave, that repeated motion. And so these points that are here are going to move down to here, 1/4 of the time period, right? So 1/4, 1/2, 75%, 100%. 1/4, half, 3/4, 1, and so on. And so all these points will be here, all these points will be here, and all these points will be here 1/4 of the time period. And so our new position for all the particles is just going to be the equilibrium position, that horizontal line right there. And that's part 4.